Thanks so much for the introduction, Razvan, and I'm very happy to speak to you all today. My name is Petar Velickovic, and I'm a research scientist at DeepMind. Previously did my PhD at Cambridge and a few research internships at Joshua Bengio's team at Mila. And previously, I originally come from Belgrade in Serbia. And my research interests are in core graph representation learning and applications. And that's why today we're going to be talking first a little bit about a recap of how graph neural networks work and what are the standard ways in which they operate. And then how, armed with this essential GNN knowledge, you in principle could have done several highly impactful applications that are out there in the real world already. So in this talk, we will be talking about neural networks that operate on graph structured data. And most commonly, these approaches are grouped under the umbrella term of graph neural networks, or GNNs. And they are quite a hot topic in machine learning research recently. At ICLR 2020, which was a very recently held deep learning conference, they were graded as the fastest growing area of machine learning research. At last year's NeurIPS, they were rated one of the top workshops. So the graph representation learning workshop was second in size only to deep reinforcement learning. And even though it started gaining traction only around 2016, 2017, it has already managed to break into the real world in very impactful ways. And here we will study exactly how this has taken place. So to begin with, we will talk a little bit about how we can process data which is defined on a graph. And there's a lot of motivation for why we might want to do this, because graphs are literally everywhere around us. Here I've given 4 very canonical examples, such as molecular graphs, transportation networks. Here you have the London tube map, social networks. Here you have the Facebook friendship graph in the bottom left, and even some places where you might not expect graphs to take place. But for example, we can even look at the connectome in the human brain and represent it as a graph. And in a way, we can think of graphs as a natural generalization of the more standard image and textual data that we often work with in deep learning. And in a way, we can think of graphs as a way in which nature gives us data in most cases. And that's why being able to process data that lives on a graph is something that is very useful for us to be doing. Just to kind of quickly formalize the mathematics and make it clear about which notation we will be using for the introduction, we will represent graphs as sets of vertices and edges, V and E. And we will think that in each one of our vertices, we have a vector of node features. So we have H1, H2, and so on for the features of node I, and they will all be grouped together in this node feature matrix H. We can represent connectivity in a graph in different ways, but I will most commonly be using an adjacency matrix, which will tell us which pairs of objects in the graph are connected. In the simplest case, it will be an unweighted and undirected graph. So this A matrix will be binary and symmetric, with an entry of 1 if there's an edge between I and J and 0 otherwise. But we can even think about more complicated objects in the adjacency matrix, such as, for example, edge weights or even arbitrary edge features. And it's very useful to think about the graph in terms of neighborhoods. So we can think of the neighborhood of node I as a set of all vertices that are connected to node I by an edge. And this we will conveniently denote as the set Ni. And as I mentioned, we can think of graphs as a strict generalization of images. If you look at an image, you can treat any image as a grid graph where each node is a pixel and its 4 or 8 neighbors are connected to it by an edge. And this spatial regularity in images is exploited in convolutional neural networks using the convolution operator. And it will be quite useful if we could somehow generalize this convolution operator to arbitrary graph connectivity in space. And just as a quick recap, here I gave a tiny animation on how convolution works on images. We have this very tiny kernel matrix K, which stores all of our parameters. And what we do is we just slide this kernel matrix across our input image, giving us different output positions as a summation of element-wise products. And through this shifting of the kernel matrix, we can obtain resulting images which respect the spatial configuration of the image, such that only neighboring pixels are directly influencing each other. Now, we might want something very similar for our graph convolutional network, in the sense that when we look at a node and we look at all the vertices adjacent to it, we might want to derive the next level features for that node by considering the entire set of the node itself and all of its immediate neighbors. And therefore, our graph convolution layer will be defined as this function g, which consumes the set of features of all the vertices in the one-hop neighborhood around a particular vertex, and as a result gives us these next level features h prime in each one of our vertices. Once we have this layer defined, we can then iterate, like stack it in the manner of deep learning, and eventually we will have features in each node that we can use to classify the nodes. There are a few challenges with deploying convolutions on graphs, however, because if we look at what made convolution layers on images very nice, well, we can identify a few desiderata. For example, the layer that works on a graph should be computationally and storage efficient. That is, we shouldn't use more time or space complexity than it takes to store the graph in the first place, which is the number of nodes plus the number of edges. We would ideally want the number of parameters to be fixed. So if I give you an image that is twice as big, it's still processed by a convolution with the same number of learnable parameters. Similarly, our graph convolution layer should have the same number of learnable parameters regardless of how big our graph is. So if I give you a graph that's twice as big, I should still expect to use the same number of parameters. The graph convolution should be localized, much like the image convolution. So we should only act on a local neighborhood of a node and not beyond that. And ideally, as we had that kernel matrix with different values in each corner, we should be able to specify different importances to different neighbors, and ideally be applicable to inductive tasks where we might have test graphs that we have never seen at training time. And images make all these desiderata very easy to implement because images are very rigid and the connectivity of an image is always the same. You have one node connected to its 4 or 8 immediate neighbors. So then it's very trivial to just define this small kernel matrix and slide it across the image as our convolution layer. If you want the layer to operate on arbitrary graphs, however, this presents a much harder challenge. And in this next section, we're going to go through the 3 canonical models in which you can deal with this problem. We will start off by trying to see how a simple graph convolution might be defined. To make things simple, we will for now assume that the graph is unweighted and undirected. So if you look at the entries of this adjacency matrix A, we will assume that it's binary and symmetric, giving us a value of 1 if 2 nodes share an edge, and 0 otherwise. And if I is connected to J, we will assume that J is connected to I as well. Then what we can do is, if we have our previous feature matrix H, if we multiply that feature matrix by the adjacency matrix, this effectively recombines the nodes within a neighborhood. And we can also include pointwise multiplication by a shared linear layer W, which just ensures that we have a sort of deep learning effect going on and we're not just repeatedly aggregating features. So to recap, at each step, we take our previous features, multiply them by the weight matrix to have a linear transformation, and then multiply by the adjacency matrix to aggregate all the neighboring nodes. And finally, we can apply any nonlinearity of your choosing, such as the ReLU or the tanh or the sigmoid. A few things, however, still need to be fixed. First of all, this update will discard the node itself. So you will not have information from the central node flowing back into it. And this means that effectively the central node's features are not going to be relevant to its own decision, which obviously doesn't make sense. So we make a very simple correction where we add the identity matrix to the adjacency matrix, which basically means that every node will now also be connected to itself. And now we can rewrite our update rule as we take features of all the neighbors, J, to a node I. We linearly transform them with this weight matrix, and we have a summation that aggregates all of the neighboring features, followed by any activation function that you care about. So this sum pooling rule is a very simple way in which we can specify a graph convolution. However, there is another potential problem with this, in that when we multiply by A, this can drastically increase the scale of the output features. Imagine a node that has 10,000 neighbors. This will give us a signal that's 10 times as strong because we're summing up 10,000 things, especially if we're using ReLU activations. So a very common trick to apply in this case is to appropriately normalize. That is, we additionally multiply by the inverse of the degree matrix, where the degree matrix is a diagonal matrix that gives us the degree of each of the vertices. So what this effectively means is, much like we have a rule that's very similar to what we did before, only now we divide by the size of how many neighbors node I has. And this rule can be summarized as the mean pooling update rule, where we effectively average the features of our neighborhood. and this will guarantee that the scale of the features will not explode. It's a very simple update rule, but very versatile and very commonly used, especially for large-scale graphs. Now, we can actually recover a bit more interesting dynamics if instead we use this notion of symmetric normalization, where we actually scale the neighboring features by not 1 divided by the neighborhood of the central vertex, but 1 divided by the square root of the central vertex times the neighbor size. And this actually ensures that, for example, if one of your neighbors is a highly connected vertex and sends information everywhere, then maybe its features will not be that discerning to what you want to do. And this will give a little bit more weight to your neighbors that are isolated and don't really connect a lot anywhere else. The assumption here is that if you have a neighbor which is very isolated, then that neighbor only really sends information to you, and therefore their features are going to be much more valuable to you than if you have a neighbor which is highly connected everywhere. So this kind of dynamics yields the graph convolution network, or GCN update rule, which is currently the most popular graph convolution layer. And it is a simple and powerful layer that you can apply in many circumstances where graph convolutions are required. Now, one problem with the GCN layer is that it only indirectly supports edge features. And one way to correct for this is to instead focus on these notion of edgewise mechanisms, where rather than have a neighbor's feature be what it sends to you, you could instead use the features of the neighbor and maybe some features of the edge to compute an arbitrary message vector which is sent along that edge. And now, once you have this concept, you can condition the messages by whatever edge features you might have in your vertices. And then what a node does is it should aggregate all the messages that are sent to it. So this yields the message passing neural network model from Justin Gilmer and others, where we first compute these message vectors, where Mij denotes the message that node I sends to node j. And it's computed using this message function fe, which consumes the feature of the sender vertex, the features of the receiver vertex, and any edge features you might have along this edge, and produces a message vector that I sends to j. So this FE is usually a very simple multi-layer perceptron, or just a simple linear layer, actually, that will aggregate the information from the sender, the receiver, and the edge to give you a vector-based message. And then node I just has to aggregate, for example, by summing up all the messages that their neighbors are sending to it. And this gives you the overall message vector from all of your neighbors. And we also add this skip connection here to kind of simplify the flow of information. And finally, the resulting 2 vectors are processed by the readout function fv to get the next level features for that vertex. And this is the message passing neural network, which is significantly more powerful than the graph convolution layer, because now we are allowing arbitrary information to flow along the edges. And to kind of illustrate what's going on here, let's see what happens if I want to compute the next level features for node 4. First, I will compute all messages sent to 4. So if I want to compute the message from 3 to 4, I will take the features of 3 and the features of 4. Here, I'm excluding edge features, but they can be added as an extra input. And this message function produces the message from 3 to 4. This message is then fed back into the mechanism, which sends from 3 to 4. And in a similar manner, we have computed the messages from 2 to 4, 5 to 4, and so on. They're all summed up in vertex 4. And finally transformed by this readout function to give us the next level features for node 4. And they're fed back into node 4, and the process can resume from the beginning. Now, the message passing neural network is the most potent graph neural network layer. You can think of it basically as an MLP of the GNN world. However, this also means that it might have some problems with scaling up, because it requires you to store and manipulate these edge messages, which will occupy substantially more memory than just node messages. This is troublesome both from a memory point of view and a representational point of view, because now your supervision signal has to optimize a lot more parameters. And that's why in practice, the message passing neural net has only seen a lot of applications on relatively small graphs, maybe up to a few hundred nodes so far. But we ideally still like this approach of being able to use the edge features to selectively recombine information. So let's work towards an approach that's somewhere in the middle. Let's look at a more generic form of the GCN update rule, where we still send these node messages along neighborhoods, but now we have an arbitrary constant which tells us how coefficient, which tells us how node j's features are relevant to node I. What the GCNs did is they defined this alpha coefficient explicitly and they kept it fixed. And this made the layer to have several shortcomings. But instead, we can let this coefficient be computed implicitly, for example, with a neural network. And if for computing this alpha coefficient, we use an attention mechanism, so this is some arbitrary attention function, which takes features of the sender, features of the receiver, any edge features. And unlike the previous message passing system, this one only computes a scalar. So it gives you one value that says how much are node J's features relevant to node I. And then much like in the transformer mechanism, you can then use a softmax to normalize all of these neighbors and give you a nice sum which doesn't explode. Now we have reached the graph attention network update rule, which if you use the multi-head attention trick, much like the transformers did, can significantly stabilize it. And currently, it's a bit of an open question whether just having a scalar in the edge as opposed to a vector gives you less expressive power. It's my belief that they're probably not as general as message passing nets, but they're much easier to scale up in terms of memory and in terms of computation time. And they're still powerful enough to reveal interesting dynamics across neighborhoods. So to recap, the key difference here is that the attention mechanism computed a scalar per each edge, whereas the message passing nets computed a vector per each edge. And here is just a visualization of a single graph attention network update step, where a vertex receives different heads of attention distributions for each one of its neighbors, and then they're used to compute linear combinations of all the vertices' edges. We also include a self edge so that the node can send attention coefficients back to itself and not lose information. And finally, the information from all the attention heads is either concatenated or averaged to get the next step features of this node. So you can think of graph attention nets as basically a transformer which is masked to operate on the graph's edges. Now I will give a very quick and brief overview as to how, once you've trained the graph neural net like this, you are able to use them for any learning task that you might care about on a graph. So we're provided as input a graph which has node features X in each of the vertices and an adjacency matrix A specifying the connectivity. Applying our GNN layer, which is GCN, MPNN, or GAT, we will have transformed features in each of the vertices, these H's, after some steps of message passing along the edges. And now once we have these H's, what can we do with them? Well, a very simple task that we can do is classifying the vertices of the graph. So if, say, I have a prediction task where I need to predict something in each of the vertices, I can have a function which is independently applied to each of the nodes to give me outputs for each of the vertices. If I want to classify entire graphs, I can first sum up these H values for all the vertices in the graph, and then apply a different kind of function that predicts the output on the graph level. And if I want to do prediction on the edges, for example, does an edge exist or some properties of this edge, I can take the features of the two vertices that I care about and any edge features in between, and then use that to predict some quantity about the edge. Okay, so this wraps up the first part of the lecture, where we just talked about basics of GNNs and the kinds of tasks you might be applying them for. And I will now give half a minute pause to give you an opportunity to write any questions you might have about these standard models before we dive into the bleeding edge and the ways in which you can apply them. And just to give you a bit of a teaser, we will be looking at applications to computational biochemistry, traffic simulations and autonomous vehicles, recommendation systems and social networks, and understanding and modeling of physical systems. And just to be clear, in all of these cases, we'll be talking about applications that have already been deployed either industrially or within impactful medical research, say. Okay, so without further ado, let's jump into some of the applications of graph neural networks that we might find very interesting. Let's start off with the computational biochemistry and medicine, because that one is going to be by far the easiest to conceptualize with the tool chain that we've built up so far. So As I mentioned at the very beginning, we can think of molecules as graphs. So a very natural way to represent a molecule is by representing it as a graph where the nodes are atoms and the edges are bonds between the atoms. And you can put features in the nodes such as what's the type of atom. So is it carbon? Is it nitrogen? Is it oxygen? You can put also the atom's charge. And on the bonds, you can say what's the type of the bond? Is it in a ring or something like that? And then we know that when we have a molecule, the way in which we compute the actual chemical functions it performs is strongly influenced by a node's local context. So what kind of edges, what kind of bonds it has connected to it. And the ways in which this is influenced is also very complicated. And this means that message passing neural networks are likely to be the most appropriate choice for processing these graphs, because we know that they have to model very complicated dynamics, and therefore these edge messages are very important as a concept. And what could be an interesting task to predict over these graphs? Well, one very important task could be to predict whether the molecule represents a potent drug. So could we use it to treat diseases? And one simple thing you can do is you can start with a known curated data set of, is this molecule going to be a strong inhibitor against a certain bacterium, for example, Escherichia coli? And this is then a simple binary graph classification task. I have as input a molecular graph, and I want to predict for each of these graphs a yes or no. Is this molecule strongly inhibiting a certain bacterium? Once we've trained this model, we can then take it and apply it to any molecule we want, even ones for which we don't have chemical evidence. So there are many large data set of known candidate molecules that are just drugs being repurposed, which means that you don't really have to go through the entire process of FDA approvals and so on for the compound itself. Like, it's already known to cure a certain disease or to be used against something. So you can take this large data set of molecules that are known to treat one thing and see if they could be used for something else, and execute your trained graph neural network on this data set. And you'll see that some of the molecules in your candidate data set have a very high response, like a very high probability predicted by the neural network that they're going to inhibit Escherichia coli. And what you can do is then you can just select the top 100 candidates and send them to chemists and have chemists investigate all of those. Maybe some additional filtering is done, but they can perform studies to see if any of these could be interesting. And it just so happens that within this top 100 predictions of your neural network, you discover a new compound that is highly potent and previously completely overlooked, as in nobody considered a compound like this or a compound that's very similar to this one. And it's been shown to be very effective against many different strands of bacteria. And this molecule I've presented to you here is halicin. So you've discovered this. You've published this in an appropriate journal, where you detail your deep learning approach with message passing nets and how you then send this off to chemists for validation. And just as a consequence, you get shared by Nature, and you get republished in the Financial Times, and you get republished in the BBC, and many other. If you search for scientists discover antibiotic using machine learning or using artificial intelligence, well, first you can be aware of that now it's actually graph neural networks that are behind this major milestone in computational medicine. And secondly, I hope that it's clear that the leap from the basic understanding of what a message passing net does to the actual real-world application with strong potential impact is conceptually not very large, because all we did is we took a given molecular graph and we trained a message passing net to perform graph classification on it. Now, to mention an emerging application, we all live in very troubling times right now with COVID-19 going on and so on. And it is very important to try to find potential candidate treatments for COVID as well. So what we can do is we can look at drugs and diseases as entire nodes in a graph where edges say the drug I is used to treat disease J. And now if we do a link prediction in this task, link prediction task over this graph, this can tell us which drugs can be used to treat new diseases. And once again, because these drugs are already used to cure something else, the time necessary to put them out on the market is far shorter than if it was a completely new compound. Now, the problem here is that a new disease comes up, like COVID-19, and you don't know any effective drugs connected to it yet. So how could you use it? How could you use this approach to predict new drugs for it? Well, One thing that we know is that drugs target proteins and diseases affect certain proteins or genes. So we can introduce protein graphs as a middle layer between the drugs and the diseases, which will tell us about these intermediate interactions that we can then use to predict direct drug-disease links. So what we're going to do is we're going to encode both drugs and diseases and these proteins in the middle layer using a graph neural network. In particular, recent research has found that graph attention nets have worked particularly well for this. The only difference is that there's an extra parameterization of relation type. That is this a drug-disease relation? Is this a drug-protein relation? Or is this a protein protein-protein relation? And for each one of these, you will have a separate attention mechanism learned to connect vertices. And once you've trained this to be predictive of existing links in the graph, so you take HI and HJ, once you pass it through this graph neural network, and you try to predict from those two a binary task, does IJ exist in your original graph? This can give you a very effective encoder for nodes. And now you can use this to search for what are the new closest drug nodes to a given disease node in terms of the H, and you can use that to recommend what are the possible candidate drugs for this new disease. And in this recently published archive preprint from this is a joint effort from many groups, including Albert Laszlo Barabasi's group and Marinka Zhitnik's group. They have done exactly this, and they've tried to embed both COVID-19 as a node in a graph and all the existing drugs and diseases as a node in a graph. And then they've just looked at, in the projection of these H's, what are the closest drugs to COVID-19's node. And here they found a list of 18 candidate treatments. And basically, what gives us kind of encouragement that these predictions are sensible is the fact that among these 18 predictions, you can already find some drugs that have been tested for their effectiveness against COVID, such as chloroquine and ritonavir. Okay, so now we're moving on to the second application, which is how graph neural networks can be applied to traffic simulations and perception in autonomous vehicles. So if you look at transportation maps, such as the standard thing that you might be looking at when you open Google Maps, you can hopefully see how we can naturally model something like this as a graph, where each intersection could be a node and edges could be roads, and then we could do very interesting prediction tasks over this graph to, for example, optimize user experience or warn them of any incoming traffic jams or something like this. In particular, one very important task to predict here is the estimated time of arrival, or ETA. This is a critical service provided by Google Maps, which, given a start point and an end point, computes for you what's the expected travel time. So how long are you expected to travel along this route? And this is important both for the regular users of the app and many other ride-sharing or delivery companies that rely on the Maps API to tell their customers how long are they going to have to wait for their delivery or for their driver to arrive. And what are the possible relevant node features we could be looking at, or edge features? We can look at what's the length of roads. We can look at what are the current speeds on the road. And very interestingly, we can look at what have the speeds been on this road historically at this time of day, which tells you whether, for example, we're about to hit a rush hour period of the day, and then there's going to be a traffic jam either way. And you can collect this using anonymized, crowdsourced, real-time, and historical traffic data, which is not as reliable as physical speed sensors, so additional post-processing is necessary. But it's still a very challenging task to perform either way, because traffic conditions can change dynamically and unpredictably, and most of the trips that users are querying are between 10 minutes and 1 hour in duration, meaning you have to make near-future predictions on how the traffic is going to evolve. And DeepMind and Google Maps teams have partnered up in tackling this problem. The way in which they've done so is by partitioning the candidate route into this notion of a super segment, which basically samples the road in chunks based on how much density of the traffic is there. And here you can see on the visualization that the road is partitioned into these vertices, where the edges correspond to node links. And then we can run a graph neural network over the graph that's specified by the candidate route, and directly from this graph predict what's the expected travel time. So we're performing a graph regression task effectively. So the overall pipeline here is that we can look at many sets of training data from previous travels. We take the routes that were taken at that time and split them into these super segments and use them as training data for a graph neural network that does graph regression from the super segment representation of a trip, and the outputs are how long has this trip taken. And once we have a trained graph neural network and a user inputs that they want to go from point A to point B, we use a pathfinder to select what are the possible candidate routes from A to B. And then this graph neural network can rank all of these routes by how much time is going to be taken to travel along them, estimatedly. And then we surface this information to both the Google Maps API for the developers that use the information and to the Google Maps application for all the front-facing users. And this was actually already deployed in several major cities. So if you're in one of these major cities in the world, chances are your travel time estimations are already handled by a graph neural network within Google Maps. And in almost all cases, this has substantially reduced the percentage of negative outcomes when it comes to travel time. For some cities, such as Sydney, this reduction was as high as 49%. And as an emerging application here, I would love to mention this concept of autonomous vehicle perception. So you have many vehicles which are in traffic at once. And to have a self-driving car that behaves well in this case, the self-driving car ideally has to be predictive of what all the cars and pedestrians around it are going to be doing in the future. And this is a very challenging multi-agent problem with many unobservables, as exemplified by these three situations. For those of you who come from Eastern European countries, you might recognize these as typical photos you might have to answer during a driving test. So to predict what's the best way to act in a particular situation if you know particular vehicles are going to act in a certain way. So Waymo and Google AI have actually recently put out a research paper on vector nets that tries to tackle exactly this problem of predicting where each of the agents, cars, and pedestrians are going to move in the environment. And what they do is they vectorize the current state of the road in this sort of representation, and then they treat each of these components of the road, such as lanes, crosswalks, and different agents, such as cars, as individual vectors. And then once they have this representation, they take each of the connected components of these vectors. So, for example, the crosswalk is represented as these 4 vectors that go in a circle. And these 4 vectors are treated as 4 nodes that are fully connected in a graph. And the same thing happens with the lanes. So here we have 3 vectors that represent an edge of a lane, and they represent 3 nodes in a fully connected graph, and so on. And same thing happens with agent trajectories. What happens then is that all of these building blocks are connected to each other in a global interaction graph. So a fully connected graph of graphs where everything kind of is allowed to interact with everything else. And the color indicates whether it's a crosswalk, a lane, or an agent. And then once you have this graph, you can run a graph neural network. In this case, they run a graph attention network style model to predict 2 tasks. First one is a self-supervised task of map completion, which is if I take out one of these vertices from the graph, see if you can predict what's the shape of this vertex based on everything that's neighboring. So this is the map completion task. And also, you can look at individual agent nodes and try to predict where these agents are going to be moving in the future for this trajectory prediction task, which is actually what we care about. So we want for all of these green nodes, which are members of traffic, to see where they're going to be moving at a point in the future. And it turns out that this vectorized approach with graph neural networks substantially outperforms all the previous approaches in a standard benchmark for traffic behavior prediction. And here we have a few visualizations of the attention coefficients in red, which show that the method actually learns to lock onto the correct lanes. And even when it makes a mistake, it still assigns a high attention score to the lanes that were actually correct. So these could correspond to cases where an agent could reliably make either one of 2 possible turns, and it just happened that the other turn achieved a little bit more attention, but this doesn't mean that the prediction was substantially off in either case. Okay, now we can move on to applications to recommendation systems and social networks. A very common task on a social network is recommendation. So if a user has some preferences, like things that they liked in the past, let's recommend some new content to the user that they might find interesting. And what you can do is you can leverage existing links, like what are the things that users are known to co-click on as some adjacency input to a GNN that does link prediction. One big issue with this is that all of our methods so far assume that the graph is processed all at once. And all of the graphs we looked at so far were quite small, so they could fit into memory all at once. But most of these social networks are quite large. So then this arises the question of how do you run a graph neural network over graphs that are very large? And the first method proposed to fix this, the graph stage method from Will Hamilton and others, actually does a rather simplistic thing, which is take whatever is the neighborhood around the particular vertex and just subsample. So randomly choose to drop a certain amount of vertices, both at training time and test time. And just once you train this kind of model for enough randomly sampled neighborhoods, you will be able to achieve performance which is equivalent to if you had the full graph in memory. And this turns out to work quite well. So at each step, you take a batch of nodes, not the entire graph, you take a batch of nodes, and for each of the nodes, you subsample neighbors and some neighbors' neighbors, and you teach your GNN to operate only over those tiny, tiny subgraphs. And once you've done this, you can scale it up even to the extreme. The recent PinSage paper from Rex Ying and others has applied this approach to the Pinterest graph, which has 3 billion nodes and 18 billion edges. And if you're not familiar with Pinterest, it's a social network where concepts like interesting things are formalized as pins, and they might have any information attached to them, such as images and text. And boards are places where people can cluster related pins together. So this gives you a very natural pin-pin graph where two pins are related if they share a board with each other. And pin features can be as diverse as images, text, or links. And what you want to do here is a recommendation. So given the user's previous pin history, what kind of pin could we recommend to that user to check out next? And one big challenge here is that just teaching a standard link prediction graph neural net is not enough, because you need to select about 100 useful pins out of billions of possible options. So it's very easy for any link predictor to just learn to say no to most options. The way in which the PinSage team had solved this is by gradually making their negative samples, so the examples for which the link predictor has to say no, progressively harder and harder. So here, if you have a query with some flower art, you know that the positive example is another instance of a flower art. And you can take any randomly sampled pin as a negative example at first. But once the link predictor starts to get a bit more confident, you need to make its job harder by giving it a negative example, which is actually quite close to the query image, in that they're both the same artistic style, but this one corresponds to a bird rather than a plant. So progressively, you need to make the job of the link predictor as hard as possible so that it can actually rank you the 100 most useful things in a meaningful way. And once they've trained the system in this way, they've performed A/B testing, they've published this paper at KDD, and they found that the user satisfaction has indeed risen compared to the previous methods that were applied, and also that the PinSage method was a direct winner compared to many other possible ways of looking at these images. And you can also visualize the different recommendations that the model is giving. So for example, if you give on the right-hand side this image of trees and tree cutting, if you look just at the visual features and predict the neighbors, you might end up with some undesirable pin suggestions, such as these pictures of warfare. And if you use PinSage, you can actually get images that are quite semantically similar to what is it that you wanted to do. And similarly, on the left-hand side, you have some images of plant growing. If you look just at the visual features, it's going to give you pictures of food, which just seem to share a lot of pixel content to the plant images, but actually are completely unrelated to the planting images. OK, and one emerging application on social networks is the detection of fake news. So social networks are quite useful, and they've simplified many aspects of our day-to-day life. But they pose substantial risks to the spread of misinformation and fake news. And news on a social network spreads quickly and widely, following a graph of user interactions. And not all users are credible. Here, you can see that actually users that are less credible seem to cluster together, creating a sort of echo chamber effect. And Fabula AI, which was a startup directly designed to tackle this problem, tackled this task by doing annotation through fact-checking. They established a data set of articles which have been subsequently fact-checked for their correctness, giving labels of either true, fake, or uncertain. And they've said that if an article is uncertain, we will just not consider it. So we'll look at only the articles for which the fact-checkers have either unanimously said that it's true or that it's false information. And once they have these articles, they will represent each article by a graph of users that have shared and retweeted it on Twitter, where two users are going to be linked together if they follow each other or if one of them retweeted from another. And you can also add any other interesting node features that Twitter might give you, such as the number of followers, to kind of strengthen your decision. And they published this paper on the archive, Fake News Detection using Geometric Deep Learning. And I will just quickly detail the approach that they've taken here. So this is one example of a news spreading graph, where red nodes are the ones that have initially just shared the article, and all the gray nodes are the ones that have retweeted it. And you have the red links, which correspond to retweeting links. So user A has retweeted from user B. And the blue links correspond to following links. And the size of the nodes corresponds to how many followers they have. So you can see that the nodes that have a lot of followers tend to create this massive cascading effect where a lot of people just directly retweet from them. And then there's a few isolated cases on the edges of the graph. And what we do then is we do a graph classification task. So we take this news spreading graph and we try to predict whether or not it's true or fake using a standard graph attention style graph classification model. So we run our graph through a few steps of graph convolution, well, graph attention in this case. We do average pooling to average all the node features, and then a standard fully connected neural network with a softmax at the end to predict whether or not the article is true or fake. And now what you might be asking is how predictive this model actually is, and more importantly, how long do we have to wait for the news to spread before it gets confident in its decision? Because one thing that's quite important is that sometimes the faster you tag something as fake, the less of an impact it's going to make. So it's very important to see how quickly the model behavior will stabilize. And what happens here is that here you have a plot of the performance of the model in terms of area under the ROC curve on the y-axis, and on the x-axis you have for how much time we waited for this information to spread before running our graph classifier. Also, conveniently on the top, you see how many tweets have been made on average after you waited for this long. And you can see that the performance is already immediately quite strong with like 0.8 AUC on average. But if you give it just 1 or 2 hours to stabilize, it's already reaching up to 90% AUC, which is something that's a fairly reliable and stable predictor. And the stabilization doesn't substantially improve as you wait for any longer, meaning that this graph neural network model is quite stable in this regard. And also what's interesting is that what you can do then is you can take the node features that this GraphNet is predicting and try to cluster them, project them into two-dimensional space, and then you can see if any interesting clusters emerge. Here, the authors of the paper have colored the users based on how likely they are to share an article that has been debunked to be fake. And you can see quite interesting things emerging where you have these red clusters starting to form, where most of these users that spread articles that turn out to be fake end up clustering with each other in node feature space, even though we never explicitly gave this credibility rating as an input feature. And this indicates that, first of all, the model is probably extracting meaningful representations of users. And second of all, we might well enough be having this echo chamber effect where misinformation spreads just because a cluster of massively interconnected users is sharing this information. And these kinds of results very quickly received the attention of Twitter, that shortly thereafter acquired Fabula AI. And now the people who worked on the fake news detection at Fabula are some of the leading graph neural network researchers at Twitter. OK, and I will quickly wrap up with an application to understanding and modeling of physical systems. This is something that I thought was quite cool. So probably most of you have heard of the Large Hadron Collider at CERN in Switzerland, which is the world's largest particle collider, important for gaining fundamental insights about particle physics. For example, the discovery of the Higgs boson was remarkably performed using the measurements made at this facility. But the problem is that in order to get meaningful data, each experiment at the collider produces a lot of data. And most of this data is not useful. So we have reached to the point where just to highlight what data the scientists should be looking at requires to use machine learning. Like manually going through all the events and selecting which ones are important is not something that scales to human analysis anymore. So machine learning is necessary before you even start to process and interpret the data. And here we have one example where out of a bunch of particle collisions, only a handful, the orange ones, are meaningful, and all the other ones are just noise that we should ideally eliminate. And in this paper, pileup mitigation at the LHC using graph neural nets, researchers from LHC have successfully used the variant of graph neural networks, the gated graph neural net from Yu Li and others, to more effectively eliminate these parasitic collisions. And this can be treated as a node classification task. Nodes are particles. You link them together by how close they are in polar coordinates and classify for whether or not they're important. Like, should this particle collision be considered for further processing? So it's a very simple graph neural net where you just take all these particles and their collisions, link them together by proximity, and run 3 steps of graph neural networks with a residual connection and predict in each of your vertices whether or not it should be considered. And if you can see on the ROC curves here, using the GraphNet gives substantial performance improvements compared to the prior art that was used for this isolation. And qualitatively, if you see the graph neural network model on the far right for 3 different cases, it learns to identify these tricky clusters of unimportant points that it learns to effectively isolate compared to the prior art. And yeah, this briefly summarizes the physics application as well, which I found quite interesting, given that like graph neural nets have already seen application at CERN. So to summarize, graph representation learning has already seen real-world application in computational biochemistry, traffic simulation, autonomous vehicle perception, recommendation systems, social nets, and even physical system understanding. And in most cases, the conceptualization step from just learning the essentials of the basic GNN layers, such as GCNs, GATs, or MPNNs, is not very large. Once you know how to train a GNN and how to use it for the 3 standard tasks, making a leap from that to how could you build an application like this is conceptually not very large. And there's many, many questions and novel applications left to be discovered. And I hope to see many of you contributing to this area in the future. And if you're interested in this and want to hear more, please join us next week for the Graph Representation Learning and Beyond workshop at ICML 2020, where we have an explicit emphasis on how GNNs can be applied in the real world with 6 strong invited speakers. And the entrance is only $25 for students, so hopefully that gives you an extra motivation to join in. And if you want to find out more, here are the links both to our workshop and the ICML website. Thank you very much, and I would be very happy to take questions both now and offline.
Cool, awesome. Thank you so much, Petar. This was an amazing lecture. I'm just going to clap on behalf of all the participants. We'll jump into the questions. Well, there are quite a few questions, so we're not going to be able to go through all of them, but let's just do a few of them live, and we're going to switch to the offline.
Mm-hmm.
Okay, can you see the questions?
Yes, I can see the questions.
Yes, perfect. So so the first question is, as far as I understand, graph attention networks are independent of graph structure. Does it still have any influence on how much, if it does, if the graph on which the model is tested is significantly different from the trained set graphs?
Mm-hmm. Okay, so I would say that graph attention nets in their basic formulation with the softmax attention will not make a substantial difference to like how your test set performance is going to be compared to training set, just looking at graph structure alone. If your node features are augmented with something that's indicative of the structure, then maybe you might see some distributional shift just because of that. But there's nothing inherent to the graph structure which is problematic. That being said, if you think that graph structure is important for the task that you're solving, then you might want to consider different kinds of attention mechanisms. Recently, I've seen a version proposed that doesn't do the softmax, so just does a summation of the neighboring features based on the coefficients. And this can actually help you preserve things like cardinality information, so how many neighbors I have or something like that, which might be important in some applications. So yeah, the basic graph attention net model will not have this problem in principle, unless if your features are structural. But yeah, like you can always play with different variants and see what works best.
Cool. Awesome. For the next question, can you change graph connectivity during training?
Yes, this is a very, very important question, actually. And some graph neural networks, especially if you have only one fixed graph, which is a big problem of graph learning as opposed to like image learning, might overfit to the particularities of the tiny graph structure and not generalize that well. So one very common trick that we're doing to help them not overfit as much is to arbitrarily drop the graph structure at training time. We actually did this very ad hoc in the initial graph attention nets paper, just did a dropout on the edge connectivity. But subsequently, this year at iClear, there was a paper called the drop edge, which theoretically formalized that this is a very useful and effective thing to do. So yes, at training time, you're more than welcome to change the connectivity. And if you do it in a certain way, it will actually give you better performance.
Cool. Next question. Assume that I want to work with graph that changes structure in time. How can I possibly do this?
Okay, so this is a very interesting question. I'm going to start by assuming the simple case where this changing of structure is known like you know upfront for your training or test graphs how they're going to change, and you can just plug the modified connectivity at each step. If you want to do this, then all you need to do is make sure that your graph neural network is inductive. That is, it can handle structures that are different from the ones seen at training time. So anything that's more complicated than a GCN in this case, so something like a graph attention net or a message passing net, is going to be able to deal with these kinds of things just naturally by construction. So all you have to do is feed a different node and adjacency matrix at every step of your processing. That being said, if you know that the structure is changing, but you're not quite sure how, this is actually a more complicated problem, and you must introduce some additional, if you want to explicitly account for this, you must either do a fully connected graph, which will connect every vertex to every other, and then you can just like let the features and the task dictate how this connectivity should happen. Or if you want to explicitly account for which edges are added, you need to have additional edge predicting networks or node predicting networks that will predict these things for you and then optimize them. But the problem is that if you don't know upfront what these actions are, you may well need to resort to something like reinforcement learning in this case to learn how to do these actions. And this is something where it might get too prohibitive. So I would, in the first instance, recommend a fully connected graph in this case, rather than doing something more tricky.
Cool. Let's do a couple more questions, and then we can take everything else offline. Petar is quite active on Rocket Chat as well. So for the next question, what dimensions in terms of number of and size of graphs are required for doing regression using graph attention network model?
Mm-hmm. That's a very good question. So I guess first it's a difference between whether we're doing node regression or graph regression. If we're doing node regression, from my experience, the graph size doesn't need to be that big. I guess if you just take number of nodes times number of graphs, if this is in the thousands or maybe tens of thousands, that should be enough. Graph regression, on the other hand, is a quite more problematic beast, and it really depends on like how tricky and how complex your problem is. But say for most chemistry data sets where graph regression is a common task, I'd say you'd need about tens of thousands of graphs at least in order to meaningfully do regression, because the problem is this one graph level regression signal must propagate into all of your attention decisions and meaningfully influence them, which can be quite tricky in terms of learning stability.
Cool. And so a last question, what's the point in keeping the same graph in each layer? In CNN, the layers might have different shapes, different number of channels, etc.
Okay, so in terms of keeping the same graph, so you don't necessarily need to keep the same computation graph. If you want to, you can have different sizes of filters, for example. You can look at 2-hop neighborhoods in different layers. It's just that these layers for graph nets, at least for most standard benchmarks, tend to overfit so quickly that by the time you decide to expand your receptive field, you have overfitted already, and there's not really a lot of point in continuing doing this. But there's nothing stopping you from doing so. As for different numbers of channels, that's actually something that's very commonly controlled within graph nets. So that's not dependent on the graph structure. That's just the number of features that you're computing with each one of your vertices. If you remember the formula for the GCN, that's the matrix W. The size of the matrix W will correspond to how many channels you're going to have in your output. So actually changing the number of channels is a very common thing to do, and I would recommend that everybody does it, because keeping it fixed, usually the feature sizes are too big or too small. So at least the first expansions should be meaningful. Yeah.
Cool, amazing. Yeah, just we have a GraphNest channel on Rocket Chat. Petar is there as well, and I'm going to send all the rest of the questions to him, and you'll get your answers hopefully in due time. Thanks again, Petar, for the lecture. This was a really great lecture.
Thank you.